Yeah, okay. Hello, and welcome everybody to the finale of this RL debate series that we have been running in the past 4 months. Today we're gonna get together with the presenters, 6 of them who presented their ideas, and we're gonna just discuss, debate, and finally end with a synthesis of these ideas. And yeah, before we get into this, I wanted to remind you that these meetings are recorded, as you know, and we're going to put them on YouTube. But there's this final Q&A session that we might still have today as well that is not going to be recorded. And before we get started, I just wanted to thank the Redwood Center for Theoretical Neuroscience and its director, Sazun, for supporting us, and also thank the presenters who gave us their time and they presented these ideas. And also thank to you all who followed us. Okay, so the source of this debate is, the original question is, okay, we have brains, and the point of having brains is to generate behavior. What is the point of seeing and thinking if it doesn't lead to action? And the mainstream approach to modeling active learning is currently, I think, reinforcement learning. And we want to investigate and examine the possibilities that RL afford us, but also its limitations. And we're going to take this in two angles, scientific understanding. Can RL allow us to understand and explain agency from a neuroscience or biological perspective? And the second goal is, can we build agents that work using techniques from RL? And I think these sets of goals, these two goals are broad enough that actually, I think most people in this audience cares about either or both of these. So it's like a pretty broad set of goals. And we have been debating this, what drives behavior question. And this is a very, very short summary. It's not fair, but I just wanted to summarize, condense the whole thing in like half a sentence. So Adam says it's reward. Eli says it's error minimization, homeostasis, or predictive homeostasis, which is allostasis. Fritz says it's information gain, curiosity, exploration, and so on. Tom says it's empowerment that allows you to have more control. Neil says, you know what, we need structured representations. That's the first step. The whole thing is wrong if you don't have that. And Anne says that it's complicated. There's a bunch of different mechanisms and algorithms running in different parts of the brain, and it's not a monolith. The brain can be thought of as a symphony. Okay, so the first part of this final debate session is going to be, we're going to take these two questions, and then we're going to ask our presenters how much they believe RL can help us achieve these goals. And importantly, this is a question about how much, because of course, we know RL can help us, but is it like substantial or is it just like a minimal? Do we need something substantially different than RL to augment our thinking to achieve these goals? All right. So the reason, we're gonna approach this question from kind of a very bold and coarse-grained perspective. Imagine this is a set of all behaviors that humans and animals exhibit. This is a pretty broad set. It's a very diverse set of types of behaviors. And we're going to ask, out of this kind of full circle, what portion can be explained using RL? There are some possibilities. Either RL doesn't explain much. It explains good enough half of the behaviors, or it actually explains like most of those behaviors. And they're going to ask the same question for all of these behaviors we want to put on robots, and how much of that can be achieved using RL. This is the question. And we're going to go now in the next slide, we're going to go start talking about the answers that the presenters gave us. Starting with Niels Leetholm. Niels, why don't you take it away?
Yeah, sure. So I guess with this exercise, I had to go at putting some of the different things that our group are currently working on and think are really key to developing. Well, we're inspired by the brain, and so we're thinking about, what are the principles that are the basis of human or mammalian behavior. In our case, particularly focusing on the neocortex and how we think that might be operating. Um, but kind of maybe spoiler, I guess the slide looks pretty much the exact same for the kind of building useful AI slash robotics, because we think these kind of same principles are going to be key for that kind of system if you want to engineer it. Um, and yeah, I guess there's a lot of things in here. Reinforcement learning isn't a huge part. I think clearly there's a role for it, but I think reinforcement has learning has had a pretty good go of it in terms of kind of seeing what we can get out of it. That was already making headlines back in 2015 with things like Atari and Go. Um, but I think it's also become clear that it isn't enough, um, even when combined with things that are arguably kind of biologically implausible, like backprop, which gives the system this extreme ability to um, kind of fit essentially arbitrary functions. Even in that setting, it stumbles with things like generalization and efficiency of learning. And so I think we need something more. And yeah, Hadi, I guess, kind of paraphrased by highlighting this idea of structured representations. And so that's something that we really focus on, I guess, with our view, which is that, already in the 80s, neural networks existed, and we were trying to get them to learn something interesting, but couldn't do that with kind of heavy and base learning rules. Um, and I guess our feeling is that there were some inductive biases that were missing, and those are really these kind of reference frames, which essentially are structured representations that you can lay down learned kind of elements in and path integrate in. I probably said a lot already, so I think I'll stop there. But yeah, I'm definitely happy to kind of talk more about some of these other elements.
Thanks, Niels. Yeah, I mean, the point of this first part is to just hear about these ideas framed through this angle of scientific and engineering goals, and also like in this visualization of like a Venn diagram. But I guess I'm going to invite the other presenters if they have any thoughts and comments they want to add here. Just, while also saying that there's this other section, the part two, which is actually designed to be more of a like a sparring situation. So we're going to have a little of that. So if you feel strongly about anything, keep it for that part. But if there's anything you want to add here before we move to the next slide, feel free to go ahead. Okay. So yeah, I guess as Niels mentioned, the engineering part is also kind of like a share is overlapping with the old one. Is there anything you want to add, Niels, here?
Sorry, my mouse turned around. No, I think yeah, I think I'm kind of happy with the summary before, but yeah,
Mhm.
essentially I'd say just the top kind of three things are really the most important. It kind of if I had to kind of rank them, so the reference frames, the unsupervised sensory motor learning, and then a modular repeated model building unit. But then we need to connect those. That's where the hierarchy slash hierarchy comes in, and we need some way for them to learn. That's where the kind of causal Heppian learning comes in. And then the other things are getting a bit more into kind of details or sort of supplementary systems that we think are important. And the kind of joint attention, that's in the biological setting, that's really just humans. And here that's more kind of supervised labels. You can imagine like, okay, your system's learned really good models of the world. Now you want it to be able to associate those with labels that we care about. And so that's kind of a very small part at the end.
All right. Thanks, Niels. Now we're going to go to the next presenter, Adam. So, yeah, Adam sent me an email that I was actually very surprised to see because I thought in my mind, yeah, okay, well, let's just present what Adam said. So he started by saying that the basal ganglia is only 1.5% of the human brain volume. Therefore, maybe the answer is the portion here is 1.55%. It's maybe too low. So Adam said maybe like in mice it's 40%, and in humans it's 10%. So let's just visualize it. And I was surprised to see this because maybe this is a straw man, and please correct me here. I thought that people who are proponents of RL, they actually think otherwise. They think that a big portion of human behavior can be explained by using RL terminology. So I was surprised to see you say 10%. Can you like elaborate a little bit?
Sure. Well, the other thing I want to say is that apparently, according to Gemini, where I got all these numbers from, mice brain volume is about, I think, 6 to 9% basal ganglia. And I think that like multiplier roughly of, let's say like 4 or 5x, it like strikes me as intuitively roughly correct, even if like the overall number is like 1.5%, just didn't seem right. And because I think that the basal ganglia do RL and the brain does a lot more than RL, it seemed like a good place to start answering this like otherwise impossible question.
Yeah.
Okay, so why did I say that humans are like only 10%? Well, like, again, to like do this like very coarse anatomy thing, like there's a ton of cerebral cortex in humans that is like doing stuff that is obviously important, that is like this massive expansion over primate evolution, and that I don't think RL has much to say about what's going on there. I think if you just like look on a more behavioral or psychological level, there's clearly disorders like substance use or addiction that are like clearly tap into RL circuitry, and then there's like a ton of other shit that like just RL has seems to have nothing to do with. Things like perception, for example, is like, whatever, some huge chunk of what we do. A lot of, motor actions in humans seem to be in the absence of explicit reward, right? I'm not always like practicing my tennis serve or like playing piano. Sometimes I'm like walking. I don't think that it's correct to think of like locomotion as RL mediated in humans, even if, as we'll get to later, like that could very well be learned by RL in robots. So I just think that humans are big and complicated, and they do a lot of things, and RL is a useful framework for some of those things, and I don't think that commits me to thinking that it's like the only framework for everything. And non-human animals, especially like rodents, are a bit less complicated. They seem easier to motivate using rewards. It seems to be a bigger chunk of their brain circuitry and a bigger chunk of just the behaviors that they are able to perform. They're not able to do many of the amazing things that humans do, like, I don't know, language, right? Which again is like not a good candidate for RL in most cases.
Thanks for the explanation. Yeah, I guess this is probably just on my part, misreading the literature or just maybe assuming things that are not true. And I just assume like when you see people of the camp of like, reward is enough, or like people who think that there's only one thing, the end goal is the reward and everything else is a means to that end, then it starts to feel like they're suggesting all behavior can be explained as some sort of reward maximization, but it seems like you completely disagree with that.
Well, I mean, I don't think I agree with the framing. So let's say that it's true that like if we think about goals on multi-year timescales, getting your PhD, right?
Yeah.
That in some sense, like your actions are working towards that goal. So in some sense, you're like doing reward maximization. I don't think it follows from that like all of the component subtasks that are required to like get your PhD are best thought of through an RL lens, right? And so it's nice that you can sort of abstract this hierarchy of goals, but as long as the sort of atoms there are not depending on reward, I don't think it makes sense to say that whatever reading up on a scientific literature, right? I don't think like RL is the right framework to think about that, even if it's in some sense like a subtask. That just doesn't seem like we gain much traction. And
this is really nice because it actually, I think, dovetails with what Neil just mentioned about the centrality of unsupervised sensory motor learning, which seems to be not very easy to model with reward maximization. So it's like there's a nice opportunity for synthesis already emerging. Another opportunity is the gap. So let's say 10% RL, 90% of behavior. You suggested in your email could be evolution, innate, instinctive behaviors. And this, if you admit this actually lends a lot of credence to people like Eli, who might suggest that these are like built-in priors, and then you minimize divergence to those set points. Therefore, it's like if the goal is to explain behavior, then actually the correct theory maybe is something else that these like cares about innate buyers.
Yeah, I mentioned the evolution angle mostly because I feel like in the ML context, things get like broken up into like RL supervised and unsupervised learning, which is like true. And like that's all you can also apply that to the brain and like you can make this course like mapping onto anatomical structures. But then there's this like huge bucket that like most of our ML algorithms don't include at all. And so I thought it was important to highlight there. Like that is really where I think most of the juice, at least in terms of delta between animals and robots or other ML systems, comes from. And yeah, it's extraordinarily complex innate behaviors that you see across animals and not just mammals.
Let's go to the next part. So you suggested in the most successful models that we see right now, like the LLMs and maybe like vision models, there's a huge chunk of pre-training. You suggested it's 50% pre-training, but then RL takes us from 50 to 90%. And I'm actually very curious, how can you justify this?
Yeah, well, yeah, I mean, I'll just sort of like put my cards. Basically, I think anything that you can build an RL environment to elicit, and that at some that there is some k less than infinity where your base model can pass that k, then I think you can throw RL at the problem and essentially get to arbitrarily good performance, right? If your rewards are verifiable, so like my cards on the table, I expect superhuman coding, if we don't have it already, then very soon. Certainly in the like C domain, we already have it. I expect superhuman math very soon in the next like few years. And I don't see a principled reason why this can't work for any verifiable domain. I think that there are some things, not maybe let's say roughly 10% of things that humans do that are not as amenable to this verifiable thing. And so or I will struggle there. And I think it's just important to note that things like sample efficiency, which are just super, super important for humans and any animal, like seems to just maybe not really matter in ML. If you like have a big enough cluster, it'll like allow you to do the thing that you want to do. I think there are like lots of interesting intermediate cases like robotics, where like there are constraints on like the physical and like mechanical engineering side as well as on the control algorithm side. And so I expect that to be, take a lot longer to get everything right. But like ultimately to fall in the same way, it's just not going to happen.
Thanks. Yeah, I guess I've been I'm getting continuously surprised by how good these language models are getting, even though in principle I agree with you that the sample efficiency is important, the architecture is important, but it seems like if you have an infinite GPU budget and an infinite planet that doesn't run out of, then you can actually just make it work. And I just don't like that, but it seems to be true. That's something maybe to discuss with Niels because I think he had really some strong opinions about that as well. Yeah, I'm still not convinced about the 40% because I think if you go back to Jan LeCun's allegory of the cake, you have these like bulk and then like cherry on top. That to me seems more intuitively correct. And even with these like verifiable domain, that's the pass at K. There was this like best paper this year that showed, it doesn't really help. It just makes it more efficient at low K, but it actually hurts at high K, like out of this, maybe like things that are like low probability. Yeah, it's sharpened. So I think to me, it seems like, just to be a little the spirit of like saying spicy things. RL seems to be just a hack that we have to replace at some point. So, but anyway, yeah.
Those are two different things. Like I'm prepared to admit that it's a hack. If hack means like humans aren't doing it in exactly this way, and there might be better ways to do it, all that is fine. But I'm not claiming that it's not a hack. I'm claiming that it's sufficient to take us to superhuman performance in a huge number of domains. Not all domains
that are verifiable. That's the key.
In verifiable domains.
Okay, cool. All right, so 40%, let's put it there. And then the gap, you're saying that humans have aesthetics and poetry and ultra long horizons.
You can tell I sent you this email pretty late last night. Anything that's not verifiable and things where taste matters a lot. It seems like that would be something. Ultra long time horizons where we know RL struggles, where it's probably better to think of it in this hierarchical way, and then the lower levels of hierarchy rather than just being like these really short time Markov transitions. We should just think of them some other way of like not depending on reward fundamentally.
Okay, thanks, Adam. Just by the way, I should just be honest here. I was procrastinating and I asked the presenters literally the night before. So they had only one day to think about it. So I'm actually really grateful that you guys sent, they've got back to me. So thanks for that. All right, next up is Eli. And Eli had this again, just it's just classic Eli, right? Everything is foraging actually. And RL is restricted to stay, go, or go, no go decisions. That's just demoting RL to this narrow domain. And the mechanism is basal ganglia estimates global capture rate, foraging theory. And the gap is you're going to have bottom-up allostasis implemented through like hypothalamus, brainstem, so on. Top-down referent configuration control. Okay, Eli, can you elaborate?
Yes, okay. So I'm glad that we've already mentioned how much of the brain the basal ganglia takes up because, so for instance, in talking about referent configuration control, I'm saying that's what motor cortex does. And there's quite a lot of motor cortex relative to basal ganglia. Now, I'm not saying that you can't engineer behaviors with RL. I'm just saying that RL, as we use it in engineering, is, exponentially discounted rather than time averaged. It's ubiquitously episodic to the point that, you have people like Charles Sutton working on reformulating RL for the continual learning setting. Whereas in biological organisms, it's actually continual from the very, very beginning. So my characterization here is really meant to point out that, what's the algorithm for active continual learning in, like let's say a vertebrate or a mammal or a primate? It's basically learn how rewarding it is to do something, and then in the long run that is, and then if the actual rewards start dropping below that rate, switch and do something else. So really, I'm saying RL in organisms like us is more of a policy selection or behavior selection mechanism than it is purely a way of acquiring behaviors.
Which is not unlike how it's operating in LLMs.
Yeah.
There's also such.
Now, also to point out, when I say, oh, everything is error minimization, that's actually pretty much the neuroscientists' way of saying everything is gradient descent. Like, those quote unquote error signals, when you look into it, they always basically form a gradient of something. So, really, like, that's not saying nothing is RL. That's saying if there's RL, it requires some kind of learning signal that gives it a direction in the parameter space, such as, a gradient, which is in fact how we implement RL in machines. We end up taking the gradient of the Bellman loss.
Well, but for that, you need value functions, and you just said abolish it. We're going to do that.
I mean, yeah, but I also said that, the basal ganglia is estimating a global capture rate, which is precisely in RL, modeling terms, a value function. Like that's what a critic is in an actor-critic architecture.
Oh, so you're saying abolish the value function name. If you call it capture rate, it's fine.
I'd take the charge of being a hypocrite there, except my point about abolish the value function is that we need to get rid of reasoning in terms of things that have no actual currencies or units. So really, I'm saying, like, let's get rid of this notion of an abstract reward function given by God, whose only mathematical properties are that it's more when the behavior is better.
Well, I'm convinced. I don't know. What do you think, Adam?
Yeah, I mean, I don't think it's given by God unless like von Neumann is God, which I'll listen to you on that, right? But it's given by
No, I mean von Neumann Morgenstern is actually like the von Neumann Morgenstern utility theory is precisely invoking like God. It's very much like mathematical Platonism saying there exists such a function, if these conditions are met of apparent decision coherence, then there exists such a function out there in the realm of forms where non-constructive mathematical objects live.
Okay, it's just saying that like there's a mathematical equivalence to obeying these axioms and maximizing expected utility. That's the way I would put it.
Right, but it's a Platonic equivalence. It doesn't tell you how to construct the function, and it
Doesn't tell you how to
you-
construct the function. That's why the success of RL, in my opinion, is so astonishing, right? Because it says if this function actually does exist, turns out that it allows you to engineer really, really powerful algorithms, such as actor critic, right? That lets you do useful things in the world. So you're right that this thing didn't need to actually be instantiated. It just turns out that by actually instantiating it, you can explain not only choice, a la von Neumann and Morgenstern, but also learning, a la the entire field of RL.
Well, you have to separate RL as a set of algorithmic tools from reward maximization as like an as an ontology of behavior. Once you have a reward function with nice units, let's say you're a thermostat, so you're just minimizing the squared error cost in degrees Fahrenheit. Great, that's a physically meaningful thing. Now you have a physically identifiable task you're trying to do, and you can use RL to do that just fine. You can use an RL algorithm to do that just fine. The optimal control people derive the same Hamilton-Bellman-Jacobi equations. They derive the same equations as RL theorists do, but in continuous time.
Sure, but you're saying I need to tell you the thing that the animal is maximizing at any given time.
Yes,
so
because if our goals are scientific rather than engineering, then we actually need to not merely say that there exists some function. We have to actually identify that function and point to its neural implementation.
Right. So in something like foraging, it would be, no, energy acquisition or net energy acquisition. In something like motor performance, it would be I have some sense of how well I did, how good that serve was. If I'm a songbird, I have a sense of how good the syllable I just produced was.
No, this is putting the basal ganglia before the rest of the brain. Because now what you're saying is there exists a task and I can identify the reward function for that task. No, the task does not pre-exist the brain. Brains evolved before our laboratory task settings tested them.
Yeah, but a zebra.
So the brain was already maximizing something or following some dynamics before we came along to segment that into, well, this is singing a song so that you can find a mate because you're a bird, or this is foraging for food because you're a hungry owl, or this is finding water because you're a gazelle. Like brains actually evolved to try and meet all of those needs at once, trading off between them and switching behaviors when it is in some sense physiologically optimal to do so. The brain decides what task it wants to do, and you shut up and watch it.
Great. So
which is nothing personal there. It's just pointing out like the difference between, so to speak, laboratory psychology versus ecological psychology or ethology.
Right. But to me, there's no problem saying that when the brain is in a given state, it treats certain things as rewarding and certain things as not rewarding. And evolution provides all the tools that the brain needs.
But what is that state, and why does it treat those things as rewarding in that state and different things as rewarding in a different state?
Because it is a machine that's constructed such that is the case. I mean, it's not that hard for an animal. If it's an animal,
right? But can you describe the dynamics and the mechanisms in detail?
I don't have the once and for all blueprint for how the brain works. Unfortunately, I will consult my friends for that. But I don't think it is like a crazy appeal to Deus Ex Machina to say that the brain knows when it's foraging versus when it's courting, and certain things are going to be rewarding when it's foraging and going to be rewarding when it's courting. We know that these are, that these behavioral states are have, brain-wide representations. It's very easy to stick a probe in and tell on the basis of what.
But it is a Deus Ex Machina to reach for a non-identifiable mathematical object as your explanation of why behavior works the way it does.
So, somehow,
if we say the brain knows and then we want to model it, we have to model how it knows using an identifiable object such that our experiments can actually pin down what's going on.
What I'm saying is that somehow the dopamine neurons know, because they burst when it makes sense for them to burst in a given context, and that can be gated by all kinds of behavioral state. And so you're right that we don't know yet how the dopamine neurons know. The fact that the dopamine neurons know means that I can say that's someone else's problem with my experimentalist hat on, right? That's someone else's problem to say how the dopamine neurons know. And now I can say, given this dopamine signal, what are the rules that are operating that reinforce a particular behavior in a particular state?
So can we interpret this as, and correct me if I'm wrong, Eli, maybe Eli's saying that that's the most interesting part, the hard part, and we have been avoiding that question forever. And that's the problem here, because the fact that dopamine neurons know is just so enigmatic and cool, but we don't know how. And then we've been avoiding that. This is like this dark matter. You used the term dark matter in your presentation. The states are extracted using perception, and then something in the brain, some mechanism extracts what goal is being pursued and what should be rewarding. All of those things are the hard questions that we have been avoiding in the scientific endeavor towards understanding behavior. Maybe that's what is the question here. I mean, Eli, is that?
Oh, yes, I mean, very much so, particularly so to slightly pick a nit, there are people studying the dopaminergic system in the basal ganglia who actually say that the dopamine neurons don't know what is rewarding. Like there are experimentalists who say, no, the dopamine neurons are encoding movement vigor and other motor variables rather than
I was going to ask
and
you,
reward
Adam,
prediction error. I'm pretty agnostic on that because it seems to me like when different experimenters are finding things that don't necessarily conflict with one another, the task of a theorist should be to try to unify those rather than explain one of the two away. But nonetheless, what happens often, when we do a concrete animal experiment, like Hadi, let's say in Jake's lab, you train the animal by controlling behavioral reinforcement such that the animal performs the task behavior you actually want them to perform. So it's not just dark matter that we're avoiding. We're actually screening off the dark matter and systematically eliminating it from our experiments, which is why we know nothing about it. We actually refuse to experiment on the dark matter because we say, no, that's just a useless, misbehaving monkey. I need him to sit down and do two alternative forced choice correctly. Saccade left or saccade right. That's what I need the monkey to do, and I'm going to reinforce his behavior until I get it. Which means you're causally screening off the decision of why he's going to act the way he acts.
I agree with your framing. I would just add, I don't know, I think I guess Anne runs experiments. I was one of only a handful of experimentalists in the talk series. I will say that there is a very good experimental reason why we screen that off. It's because we basically no one has yet come up with an experiment that would really allow you to ask in animals the questions that Eli is posing. So I think that they are very interesting to explore theoretically, but it's not as if I don't think people have just been ignoring them because they found them uninteresting or like they don't realize that like there's dark matter there. So I use that term.
So
to highlight the experimental challenge.
I completely agree with you, actually. And what I would say as a theorist is that we need to step up on our side and start describing things in terms of identifiable variables. And I don't mean identifiable in a colloquial sense. I mean it in like a mathematical statistics sense. If you have a non-identifiable parameter, then maximum likelihood fits will always give you some ostensible value for the parameter, but they won't guarantee a one-to-one mapping between data and parameter. And we need to do the work as theorists and data analysts of saying, I'm going to refuse to use something that doesn't give me, a one-to-one fit, because only then can we go to an experimenter and say, if you can give me data on this, I can identify something about what is going on in a theory-driven way. And then my problem with reinforcement learning and the value function, abolish the value function, yes, I know, is that's not an identifiable quantity. So then we're going to experimentalists and we're saying behavior is explained by, a theorem from the 1940s, which says that assuming the animal is acting rationally, there exists some function describing that behavior. Okay, how does that help an experimentalist?
Yeah, I think I kind of agree with your criticism towards us theorists that, it reminded me of this paper from Ann Kennedy where she talks about how theoretical neuroscience has room to grow. That's the title of the paper. And then she talks about how theories are have been mostly reductionist in their nature. And we don't have a nice, fully kind of like closing the loop of action perception in a nice theoretical framework that actually works and connects back to data. So until we provide that, I don't think we can point fingers to experimentalists and accuse them of avoiding the dark matter. So
Yeah,
okay.
Anne has also gone on the record saying that theoretical neuroscience doesn't pursue enough in explaining subcortical processing.
Mm-hmm.
And I'd really like to give her a big thumbs up and a hearty agreement there.
Yep.
Experimentalists have been recording from the basal ganglia, from the brainstem, from the hypothalamus, for ages in animals. And we theorists stick around in the cortex.
Yep. It's easy. Okay. So just to conclude this first half, give us a percentage number. Anything between 0 and 100.
Let's say 10%.
10%. Okay.
After all that, you
Synthesis. Agreement.
You-
Okay.
Eli, can I get a clarification? What classes of algorithms are you putting in referent configuration control?
Let's say hierarchical PID control.
Okay.
Like,
I see.
there's even on the engineering side, there's very, very good engineering work showing that if you essentially use RL to train some kind of, modular multi-embodiment like robotics model, it will learn something that is more or less akin to hierarchical PID control or glorified hierarchical PID control, which is what active inference really is.
Right.
Or model predictive control with, a hierarchical thing like.
So something like, in Boris Sutkin's work, he assumes a kind of set point and you want to like minimize your distance to the set point, right? Would
Yeah,
that sort of fall into this? Yeah.
Yeah, that's what the stretch reflex for individual muscles in the spinal cord actually is. You tell the muscle, what should be the set point in length and how much tolerance should it have for strain, for error against that. And that gives you your alpha and gamma motor neurons.
I see. So from your point of view, you still have to explain where reference comes
Yes,
from or where set points come
yes.
from. I'm still interested in like you elaborating more on that as a technical problem.
That's where the whole abolish the value function thing comes in, is that ultimately motor cortex does synapse directly onto the spinal cord, so it can drive movement directly, but of course frontal cortex and insular and cingulate cortex are ubiquitously talking to the subcortical limbic structures that ultimately are sort of in charge. So it's not like you can, you could probably say that, for instance, prefrontal cortex, if you believe in the canonical microcircuit, it has the same algorithm as, M1 or somatosensory 1, but it's working with a different data set and talking to different structures below it. So that's probably going to function pretty differently.
Any other thoughts before we go to the next? For engineering, Eli said, it's useful only for tasks with nested expectations, complex MDPs, MDPs, and the gap is real-world control, and we can address it with classical control or model predictive control. Eli,
Can I pose a question?
sure, yes.
Why did robotics fail until mostly recently, given that it had all of the tools of classical control theory that you're pointing to here? Or do you dispute the premise of the question?
I think I somewhat dispute the premise of the question.
Okay.
You know, like certainly RL-driven robotics failed, but when you custom programmed the controllers for robots, they did complex behaviors just fine. You know, think of the difference between training a drone via RL and Boston Dynamics. It was always a matter of how much, you know, obnoxious human work did you put in to get a sophisticated behavior out. Now, actually, LLMs are making a big, big difference here. So what I do want to say is one of the interesting things we've discovered with language models and foundation models is that you often don't need nested expectations. You know, often you can just do autoregressive maximum likelihood and KL control. So what people call RL for, you know, LLMs is actually Kullback-Leibler control, which means that you're essentially solving the equations in such a way that you get rid of the nested expectations and turn it into one big expectation over the stochasticity in the next token distribution. Or, you know, effectively a single probability distribution over trajectories instead of nested probabilities over each single Markov decision process step. And when you do that and then use KL control so that you're penalizing, you know, deviation from the pre-training distribution while still rewarding something with, you know, big complex models, it turns out that you can get, you know, pretty interesting behaviors pretty easily.
Any more thoughts and questions from other presenters?
I mean, yeah, I guess at some point I want to talk about the kind of, but I mean, I think it's more towards Adam's point, and it sounded like we're going to get to that in the second part about, yeah, kind of what can we solve with from an engineering perspective.
Yeah, there's a part where we start disagreeing even harder.
Oh, sorry.
No, it's fine. Okay. So, okay, before we move on from this slide, Eli, give us a number for the goal to percentage.
That's going to depend on whether we count LLM KL control as RL.
You mean like in fine tuning?
Yeah,
Is that RL?
yeah, like, is that RL?
The energy is just the likelihood
Well, I
plus
mean,
KL.
KL's is what it was supposed to be, the original mathy way. Now it's just PPO. So
Okay.
if you call, you know, clipping.
Let's call that.
Yeah,
Okay, let's call that RL.
Okay, then let's say 80%.
Oh, wow, okay. Nice. All right, next up. Yeah, I should mention, I mean, I told you that I sent this question literally the night before, so the presenters didn't have enough time. So, Anne, if you're there, do you have some thoughts that you would like to share?
Hi, yes, I'm here, and sorry I didn't send the slides, and so I arrived late, so I missed most of the inputs so far. Can you hear me?
Yes.
Okay, great. Yeah. So I think the first portion is what portion of behavior can we ascribe to RL?
Yeah, exactly. Yes.
Yeah. I mean, I think it's also going to depend on your definition of RL. So yeah, so I'm not super comfortable just giving a number. I think it's much smaller than is made of in terms of human learning, at least. I think there's many like multiple other processes that play an essential role to learning behavior that are not RL. So if by some definition, I would say, I don't know, 10-20% in humans. By some other definitions, and maybe agreeing a bit with Eli, I think there's many other processes that can be reframed as RL algorithms, but that won't match, basal ganglia dependent kind of processes. And so if you reframe it as like what is the computational algorithm, then my number would go up to some degree.
Thanks. Yeah, I just want to clarify. I mean, I know that this is such a difficult question to answer. It's like one of the most complicated. The brain is the cliche is that it's the most complex thing in the universe, and it generates this behavior. But I guess I just wanted to see if we can actually have a coarse-grained view of different presenters' perception of how this is. So you said I'm gonna put down 10 to 20% for you.
Sounds good.
Yeah, for scientific. Now, what about engineering? So building things, building agents that work.
Well, so I'm not going to claim any expertise there. Um, that said, my impression, which is going to be very much an impression based on what humans do, is that it shouldn't be that high of a number either, as long as you define RL again in a somewhat specific way. Yeah. Essentially, I feel like, any improvement we're seeing in robotics, AI, dependent on RL, like crucially depend on engineers adding lots of structure on top of the part that is RL for it to work really well. And so you could still call that RL, and then, my number goes very high. But if you think that all those add-ons that are necessary, like putting various structure, engineering, memory or other things like that, are not part of the core definition of RL, then I think it's a much lower number. I don't know, 30%.
30, okay. Thanks, Anne. I guess you have written extensively about what RL could mean in different settings and
Yeah.
what these specific terminologies within RL could mean, like model-based, model-free, all of those. You've written a lot about that, and I know that this is very nuanced. So, but I wonder if there is let's say a canonical definition of RL that you actually think for you is more canonical, more correct. I don't know. Is there any such definition that you use yourself?
No, I don't think there is. I think that actually a root cause of talking past each other is really that we use one word that has many meanings in different contexts. And I just don't think that the engineering, sense of RL is the same as the behavioral one or the neuroscientific one. And so I rather than, like saying like this is the right definition, I think people should say, like the RL family of algorithms or the RL behavior or, the RL, brain network or something that like have just more precise terms rather than just using RL.
Thanks. Yeah, this actually reminds me of reading a blog post from Ben Recht, who has some strong opinions on RL as well. Who's a professor here, so I'm gonna try to invite him in the future to come give us a talk. So, okay, thanks, Anne. Anything to add or any comments from other presenters?
Just Hadi, let me go maybe next because I have to leave early, unfortunately.
Absolutely, yes. Okay, let's go to. There you go. You are actually next.
Okay, great. Yeah, so I find this for me, RL it's on the algorithmic. It's an algorithm, and I agree with Eli. It is phenomenological because usually the reward is not well defined, but of course you can put in all kind of things that work, and then I think it has a role to play. I would agree with the 10% for scientific. And but let me elaborate a little bit for my engineering prediction. So I think to understand or to build computational devices like brains, you need a theory that is a hierarchical theory, as pointed out by David Marr. And it has kind of three levels. It has a computational level, it has an algorithmic level, and it has a kind of a hardware level. So you need on the algorithmic level, this is where RL fits in. But I think to understand behavior, we also need a computational level description of behavior. And that's, of course, very, very hard for animals. And we often get it wrong because we study animals in a certain context, in a certain experiment. As Eli pointed out, the experimenter tries to force the animal to do a certain behavior that the experimenter wants to study. But in free behavior, what an animal is doing is very complex, and it involves many different things. Think about a migration bird just deciding to go out into the open ocean. You know, how can we explain this? So I feel it somehow, to understand behavior, we need to put it in a context. We need a computational level description of behavior. I don't think we have this for natural behaviors. We have it for some behaviors. We have it for laboratory behaviors, definitely, but we don't have it even for simple animals. We don't have it entirely. And for that reason, I would say in engineering, maybe RL plays a much bigger role than 10%. But this is not because then the robot is really reproducing behaviors of real animals. It's because we wanted to do a certain thing. This can be well described by a reward function. And then, of course, it also plays a bigger role. So I think this in a nutshell. Also, I want to maybe say I don't believe that everything is that behavior can be described by the drive of curiosity. I think also this is in the context of making first contact to a new environment. This is where curiosity-driven behavior becomes important if you want to investigate something novel, and curiosity-driven behavior is nothing else than actually optimal experimental design in statistics. Then this becomes important. I don't think that empowerment is too important. It sometimes can be important in certain tasks, but again, also in a certain context, it is important. But I think there are these different contexts. So for example, a monkey, when put into a recording chair, is very, very hard to actually put into a context where it wants to explore. A monkey works for Jews because it's an uncomfortable situation in the recording chair. It is confined. It doesn't want to do that. So our colleague, Jackie Gottlieb, she wants to study explorative behavior in monkeys while recording from their brains. It's very, very hard because they work for Jews in this context. That doesn't mean they always work for Jews. So I leave it here, but that's kind of my take.
Thanks, Fritz. What about the percentage number for engineering?
Higher than 10%. But again, this is because we want robots not to do really natural behaviors like animals do. We want them to do certain specific things. And then, yes, that might be, for this, a reward function might be a much better description. And then, of course, the importance of RL goes up.
But what about a number?
Of 40%.
40.
I don't care. It's bigger than 10%.
Sorry. No, okay. By the way, when do you have to leave? Because you made some excellent points, and there's some
I have to leave in 10 minutes.
10 minutes. Wow. Okay. Yeah. Because I would love to actually hear you discuss empowerment with Tom, because like you are the two of you have this like notion of exploration, kind of curiosity built into your frameworks, and it would be nice to understand.
Right. Yeah, let me say something more about empowerment. Empowerment is this basically maximizes the mutual information between actions and sensory inputs. And I think that's sometimes important, but often not. So for example, if you do pole balancing, it's certainly not that. It's an interesting dynamic state of this pendulum when it kind of stands on its head, but you want it. You want your sensory input to not there's a very low mutual information between your actions and the sensory input. And so I think Yeah, sometimes this can be important, but again, it depends on the context. I think curiosity is a more fundamental thing. So if you really face something novel and you need to understand how it works, how it functions, how it behaves, then you want to do something like optimal experimental design. That seems to me more fundamental than empowerment, that you sometimes in some situations might want to do, but there's many other examples where you don't want to do this. But anyway, that's my take. Maybe I'm overemphasizing curiosity here. I mean, my definition of curiosity, which is really optimal experimental design.
Tom, would you like to chime in?
Yeah, I guess, let's see. Oh, yeah. Yeah, I guess I would say that I think of empowerment as fundamental just because it's the only kind of function that I know that can make context sensitive judgments. So I view that as like a hard constraint of like, Eli was talking about earlier about how we actually need hard mechanisms for, why something is valuable in a certain state and not another. And I think that empowerment is basically necessary for that.
Yeah. So why is empowerment the only information theoretic measure that's can do
Well,
that?
I
don't
mean, I think
understand.
you can have lower bounds or something on empowerment, like just raw reachability. But basically, I think it's the only thing that scales to high dimensions. So I could see, just doing mutual information, but not maximizing mutual information. But that would be like a lower bound on empowerment.
I mean, exactly. So this maximization, I don't see this very meaningful. Yes, of course you want to figure out what actions, what you're not so much interested in the null space of actions that have no effects on all your sensory inputs. I agree with that. But I think that to maximize this is too compulsive. It does not really.
Yeah, well, I mean, it doesn't
I
have to
don't see
be.
a necessity for that, but
Yeah, so I'm not advocating for the idea that this is like something that's happening all the time, but I do think that you have to explain the emergence of valuable things, and you can only do that in high dimensions of variables. So I'm mostly just calling attention to the fact that there's no other option. You have to be able to do a kind of credit assignment to say, why is this thing functionally significant to an agent? And that's, to me, a hard constraint on theories of intelligence.
yeah. So I mean, again, I'm not saying I still I mean it I can see that in a certain context also empowerment is important, and I would also I agree with Anne. It is more complicated. There is not a single objective function, but there are just different contexts, and we still do not understand behavior fully enough, how we navigate all these different contexts and how even very small brains can navigate a world, the same complicated world that we sometimes struggle to navigate with big brains, right? So I mean, there's I'm just advocating for this view that you cannot just stay on the algorithmic level, but you have to go up and down in the MAR hierarchy to understand what's going on and what's the function of the brain. And in this, we are still struggling to describe the computations of all the different natural behaviors, I think, of very simple animals still.
Yeah. So I guess since there was this part coming up in 2 slides actually. that we were going to challenge each other's views and then kind of stress test, the presenters and their beliefs about their framework. But since Fritz has to leave, I'm gonna actually just, I don't know, Fritz, how many more minutes do you have?
About 5.
Okay,
Sorry.
let me challenge you with one question I had prepared to ask you, and I want to hear
Yeah.
curious to hear your
Sure.
thoughts. When you presented your experimental results, you showed that just maximizing predictive information gain didn't really give you any empirical benefits until you introduced some sort of value function sort of thing, and then had some sort of Bellman optimality equation. Then it started to work.
Right.
Someone from the yeah. So someone from the standard RL camp might just say that, oh, you're just doing RL, but you just have this sophisticated information theoretic Bayesian definition.
Yeah, of course. Of course, you can always say, predictive information gain is just a reward function. It's not a constant reward function, right? Because it changes, it goes down with your internal level of knowledge.
Mm-hmm.
So, but yeah, it's just reinforcement learning with a variable reinforcement signal that actually depends on your previous actions.
Oh, okay, so maybe
And in that regard, I consider reinforcement learning is if you cast it wide enough, then it is really a very interesting and helpful algorithm that we should not dismiss. It's no, I'm not saying there's any mystic about this about these information theoretic measures.
Thanks for clarifying. I guess then the next challenge would be to go up or down in the MAR hierarchy and then try to see which kind of neural circuits could implement that. Then we could go look for measurements in the brain.
Right. And I mean, what I think, maybe one last comment on the MAR levels, what I also really think is important, we are so representation and algorithm focused usually in theoretical neuroscience. And we often also really, we should also consider more efficiency in terms of, energy, metabolic efficiency of computation. And this is kind of this interlinking of the algorithm with the hardware, with the biological hardware. And, this has been spearheaded by Carver Mead with neuromorphic computing, but I think this is also for neuroscience very, very important. We cannot just think about algorithms entirely dissociated from the hardware they run on.
Absolutely. As you know, I'm a big fan of these energy-aware theory of computation. So we need to make that work. Okay. Anybody else has any thoughts or questions? Fritz. Okay, we can then move to the next slide.
Okay, thank you guys. I will soon tune out. I'm sorry about that. Would love to hear. I will watch the recording.
Thanks for joining us, Fritz. Have a nice day. Okay, Tom, would you like to go next?
Sorry. Yeah, sure. Do you want me to give percentages or upfront?
Yeah, I mean, let's start with numbers. That's a lot easier.
I guess scientifically, it is hard to partition the space of behaviors. I'm going to complain about that, but I would say scientifically, I don't know, maybe the mechanisms of RL, such as I think like TD learning, are very useful. But ultimately, I would say that 20 to 30% maybe by mechanisms like that for behavior, like observable behavior. But I would say that, just to reiterate again, I think the most important unexplained thing is, how do you invent value or how do you justify long-term goals, such as moving to a new city to start a new career or something like that. And I would say that RL has 0% chance of explaining these types of things.
Right. It seems like goal selection is emerging, or just being able to tell what is right and what's wrong in your context. It's one of the most difficult, unsolved challenges. What about the engineering side?
On the engineering side, well, if it's robotics, I would say that it's very high that RL can take care of it. As long as you're not making an open-ended, system. But that's different from maybe a notion like AGI, which I think involves inventing value or computing context-sensitive value. So if it's AGI, I would put it at closer to zero, like 10% or something like that. But yeah, for robotics high, like I don't know, 80% or something like that, just because you can use RL as a hammer with lots of computation.
Thanks. Do you want to elaborate? So one thing that I wanted to ask you is that you're presenting this alternative theory that deviates from standard RL. And I wonder, your goal was, as you presented it, you wanted to come up with, you make something that is modular or compositional and address those conceptual or mathematical theoretical issues existing in standard RL. But I wonder if we just consider these two goals, scientific and engineering, how much do you think your framework can help us make progress that we could not otherwise with RL?
Yeah, I would say that it could definitely help with theory about how you reason about trade-offs in sort of like mutually exclusive goals or non-stationary value. I think empowerment is essential for that kind of thing. Like Fritz, you just mentioned that, information gain is a kind of non-stationary reward or something like that. But, if you go, that's very hard to like formalize at the level of Bellman equations. And there isn't really good theory about like, how should your value function adjust over a lifetime or something like that? How do you, if you're getting rewarded for learning a piece of information that's going to basically have an effect on your value function in the future. And I don't think that there's any really good theory about how to make RL handle sort of like lifelong learning and things like this.
Thanks for clarifying. Any other thoughts and comments from the other presenters? Okay, now
No. Hold on. I was gonna ask something to Tom.
Yeah.
Okay, ask.
Okay, so Tom, actually, how much of an impact do you think that, your like option kernels, stochastic option kernels, I think they were called, and RL methods are going to have engineering wise, considering that it turns out with LLMs, we can effectively just do linear RL or KL control. So now there's just a distribution over trajectories, which we are learning to model autoregressively, and we don't need the nested expectations. Like, does that change your mind about anything?
Well, I mean, you still have to put in the reward functions to do that, right?
Well, yes, but now you can evaluate a lot of these information theoretic goal functionals that you were originally hoping for without doing nested expectations. So in some sense, your thing got a lot easier, and in another, it might have, I don't know.
Yeah, I mean, I don't know how to think of that in terms of option kernels. Is that, did you have something in mind in terms of like, how do option kernels help with this?
Well, or, if the standard RL scenario in engineering shifts from being nested expectations in an MDP over to, a trajectory distribution that we just model, then what does that do for, does that make stochastic option kernels and similar things more scalable?
I have no idea how I would put like option kernels in a sort of LLM type situation. I do have ideas of how I would scale it in a sort of world model scenario, but I find it very difficult to figure out how you would do control theory in an LLM. I did just see something like on Twitter today about like controlling LLMs in a sort of hierarchical RL situation for like multiple goals. So I think that people are just starting to work on this kind of thing.
Yeah, was it this paper out of Google? Yeah, it was.
Yes.
Okay, we're all talking about the same thing. Okay.
All right. We might run out of, we're running a little short in time, so let's just move ahead and get to the exciting part. So here's the part we're going to challenge each other's views. And I'm going to ask the other presenters, for the next few slides, we're going to just isolate one of the presenters and ask the other five to attack him or her. And just come up with, speak your mind. I don't know how to inspire this, but like if there's anything that you just really don't buy, or if you think it's just absolute nonsense in their presented views, please speak freely, because we want to just ultimately like identify bounds, the domain of validity of these ideas. And for each of you, I have prepared one question that I will ask myself, if there's time. But yeah, with that, let's get started. It's your first. Okay. Anybody wants to throw a punch at Niels? I do have a question. If nobody else wants to go, I can ask.
Yeah, please.
It's related to what we just briefly discussed with Adam earlier. You had, among the six of you, you had the strongest opposition against transformers, scale, and backprop, and it was very, very strong criticism. But unfortunately, I mean, I'm actually sympathetic to that view, but I'm also looking at the empirical results delivered by this approach, and therefore it makes me hesitate and kind of really doubt my initial prejudice against this type of approach. So I wanted to clarify, do you think that this like scale is all you need, like transformers, like just throw a transformer with a lot of data and compute at a problem and it gets solved? Do you think that is a fundamentally flawed and it's not going to get us to AGI? Or do you think that it's just a waste and we can do better in terms of like sample efficiency and energy efficiency if we do structured representations?
Yeah, so I think, and this is kind of also what I was going to say, to kind of follow up what Adam was saying, that, I think from a certain viewpoint, we probably don't disagree in that it really depends on what you're trying to solve. I think, yeah, in your email prompt, you mentioned AGI, but there are loads of tasks out there that obviously deep learning is really good at. There's many tasks that deep learning is, better than humans ever will be. If you're talking about taking genetic sequences and predicting the structure of proteins and things like that. But the problem really is when you look kind of beyond these what are still narrow domains, then I think that's where you really run into issues with deep learning, even when it's even when RL is supercharged with deep learning. And I think there's examples which maybe came up when I presented about specifically in reinforcement learning, where models that are superhuman at Go, you can develop an adversarial strategy, which under no circumstances would fool even quite an amateur human player. But I think that example points to something more fundamental with deep learning, and which you see actually a lot in the perceptual domain, the most classic being adversarial examples. And we still don't know exactly why adversarial examples exist. We don't know how to prevent them. But personally, the most kind of convincing result I've kind of seen around that was this paper from 2018, Gilmer et al. From Google, where it was a really simple toy task where they basically had kind of two data clouds, kind of a circle in the middle and a ring around it. And then, so the task is to learn a decision boundary that's just a circle, basically, that separates those. But then they pushed it into a very high dimensional space, something like 500, and in the kind of input dimension. And they basically show that if you give it hundreds of millions of data samples, you will get 99.99999% accuracy on this. But if you then go in and look at the decision boundary, there are tons and tons and tons of places where the decision boundary does not adhere to the actual separation of the classes, where it goes off into the other kind of data cloud. But the space is so high dimensional, you're just so unlikely to sample from those areas. With adversarial examples, we're able to use gradient descent and the fact that we have access to all the gradients in the network to identify what those regions are. But kind of taking it back to your kind of earlier question, I think this just kind of points to this general brittleness and kind of alien quality of deep learning systems. And from a more practical point of view, take coding. Yeah, in some ways they're kind of superhuman. They have access to or have ingested and kind of can recreate all these different libraries, all these different examples. But in general, we're not letting them, run wild with our code. Vibe coding has kind of the reputation it has for a reason because, fundamentally they're unreliable. It's very different. So I think if we're actually trying to solve, AGI, open-endedness, something that can go out in the world where the state of the world is, non-stationary and can adapt and all these things, then I really don't think we can at all. I really don't think we can take just deep learning and kind of tack reinforcement learning on. But if we want to create a StarCraft player that can operate within certain confines and people aren't allowed to do weird things like shift the image by a few pixels, which might actually be sufficient to totally ruin the system, then sure, it's great. And it can explore and kind of develop some interesting kind of strategies in that kind of setting.
Thanks for elaborating your position. I mean, I mostly agree with you, as you know. I just want to push back a little bit on, for example, the adversarial example you mentioned. I want to highlight a paper from Robert Geiros. I don't know how to pronounce his name, Geirhos. He's from DeepMind, and they recently published a few months ago, like late 25. They published a paper. They call this video models are zero-shot learners and reasoners. And they just demonstrated that these models that they kind of generalize out of distribution. They don't exhibit those failure modes that you were discussing. They even show interesting behavior in sort of like perceptual illusions that we thought that only humans would understand. And this is the same guy who published this very famous paper like ImageNet trained CNNs are biased towards texture. So he's been on this for 5-6 years. And now he published this paper last few months ago about video models are zero-shot learners. And these are kind of the examples that I keep seeing, and it makes me doubt my strong beliefs that inductive biases that are brain-inspired are going to be significant in our quest towards AGI. But who knows? I mean, I haven't looked at that paper in great detail. So I just wanted to bring this up because I think it's too easy to dismiss these powerful performant models, and you just wait 6 more months, and they just keep getting better and better and solve problems that existed 6 months ago. So I don't know. Do you think have you?
Yeah.
Yeah, I don't know.
Yeah, no, I mean, I agree. It is always, it does often surprise you. And yeah, and Garris, he does often do really cool papers, and that, I mean, that was an interesting one. I think amongst other things, I think it's hard for our intuitions to kind of understand just the true scale of data that these systems are ingesting. And I think that kind of interferes with a lot of this in terms of kind of what seems kind of magical and what seems like generalization may not be as kind of profound as it seems on the face of it when you really think about the scale of data that's ingested. And I think as long as that's the case, and as far as I'm concerned, that has never changed over these last years. We've shown that they can ingest more and more data, but no one has shown that suddenly, okay, no, actually now the data kind of bottleneck or the parameter bottleneck isn't an issue. Um, as long as that's the case, then it's not going to be this kind of open-ended system that can deal effectively in a non-stationary world. And so, again, I mean, deep learning is a powerful tool. It's not going away. There's going to be lots of, I mean, there already are lots of situations it's useful in. But yeah, it's maybe another way of putting it is, to me, the scaling laws, it's kind of interesting that it seems that it would seem mysterious because in some sense, the more you sample data from the internet, the more you scale that, the higher the probability that the test distribution falls within your training distribution. Um, but then also unsurprisingly, you kind of have to scale that exponentially because of repeated data and all that in order to kind of eke out more of this sort of leakage. Um, so it's again, if you have infinite data or near infinite data for the particular task in mind, and it's going to be constrained, it's going to be stationary, and all these things, then sure, it's useful. But I think if the goal is AGI, then we have to look beyond that.
Yeah, thanks. I agree. I guess the data leakage is a real problem, but also efficiency and the fact that we live in a finite planet. This can't go on forever. Okay. I guess we're also running a little bit behind in time, and we already had a bit of, had some discussion, right? You should skip, I think. Sure. Yeah. Oh, maybe like, okay, do you want to, is there anything in Eli's perspective that you find not very convincing?
Oh, Eli and I already went back and forth enough. I think other people should.
Okay.
I guess, well, I wanted to ask Eli a bit about, yeah, I'm just curious for your view on the kind of engineering one. I think you talked a bit about kind of classic robotics control, and I agree in the context of, yeah, Boston Dynamics was just a lot of hard engineering and it could do kind of amazing things. But again, it wasn't, a flexible, open-ended agent that could go out and interact with complex objects in the world. Yeah, it was still kind of quite constrained. So I'm curious how what your view is really, if you look at that kind of broader question of AGI, and I guess part of the issue we could discuss what that means, but yeah, AGI for lack of another word.
Okay, so being nuanced instead of spicy, my actual view is that on the engineering side, what seems to work is usually a mixture of RL at the highest levels of abstraction, then underneath it, something like model predictive control, and then underneath that, classical control. Where I've seen layered control architectures used in real engineering, that tends to be how they go. Or sometimes at the highest level, there will even be something like temporal logic, which then gets synthesized into, a cost function for the model predictive controller to follow. But in general, the impression I get from robotics engineers is that when you want something to actually work, you do MPC on top of classical control.
But then to kind of Adam's point, robotics had some cool demos, but we still don't have robots that can clean our home or reliably fill a dishwasher. So what's missing? Is it just not enough human hours engineering these components, or?
I think so. Again, this is just an impression, and I am not a full-time control theorist, but my impression is that the field of robotics engineering and controls engineering is only starting to really get to grips with having these hierarchical systems. Whereas in AI, hierarchical planning systems are are an absolute classic that everyone learns about in undergrad and grad school. And I think that as we get a better synthesis of those two communities and, the tools that they've developed, we're going to start finding it easier and easier to say, analogously to Jan LeCun's cake, right? Here's a little bit of a cherry of RL or task-based, like language model type reasoning on top. And then underneath, here's, a whole lot of several layers of like MPC or something similar. Like a lot of RL algorithms are actually MPC underneath. I'm thinking of TDMPC, temporal difference model predictive control, which has had two different editions. For sort of the model-based stuff in the middle, you are effectively using model predictive control. And then at the very, very lowest level of individual actuators, you'll tend to have something more like classical controls. So you'll stabilize your individual effectors with classical control, then you'll operate them with, some carefully engineered, but ultimately some kind of carefully engineered algorithm that basically amounts to horizon-based planning. And then at the very, very top, you'll have a cherry of, either logical reasoning or RL that tries to direct the system underneath it.
Okay, yeah. I feel like I'd still be interested to hear kind of where the sort of perceptual richness that, at least I think is necessary to act intelligently would come from. But I also appreciate maybe for time, I don't know.
I mean,
yeah, we could always chat on the
yeah,
offline or
I
something.
think this would
Because
be
yeah, no, I'm just genuinely curious.
this would be a good subject to chat online, because what's tended to happen is that the people who study perception in terms of engineering and computation are sitting in a different lab from the people studying robotics and controls, right? So if you
Right.
then ask, well, how do I take a foundation model for perception and fuse the perceptual representations with the planning and control representations, all of a sudden it's interdisciplinary. And I think, this is maybe a place where neuroscientists should kick a few butts and say, hey guys, like in nature, those were never engineered separately and then passed from one module to another. They were always interlinked.
Right.
But it's ultimately a matter of, getting people together and getting, some fusion of the work, because I don't think mathematically there's some fundamental barrier between, perceptual reasoning and control reasoning. It's a matter of, how do you get rich representations, plan with them, like have everyone in the room understand what you're doing instead of getting confused. It's sort of a people problem, in my opinion.
Adam
Cool.
has a
Yeah,
question.
thanks.
Just on that last point, I mean, I think that I mean, it's a great point, but I would just add that to me, it's easier to conceptualize how you do this in an RL framework, or more generally like an ML framework, where you know that it's going to be a neural net of some kind doing the perception. I think we would agree on that. And so rather than translate it necessarily into a bunch of control theory primitives, you just do something more end to end. And then the other thing that I just wanted to get on the table, I'm not a roboticist, and so I don't want to feign expertise here. My impression of the last year or two in robotics is that people have found that as like NVIDIA's simulation environments have gotten a lot better, and as they've been able to scale these with a lot more compute, and people have just found that very simple RL algorithms like PPO just seem to work, and they are getting much more transferred like sim-to-real than they used to. That like this is the reason that you now have like bipedal robots that can walk over uneven terrain, where Boston Dynamics wasn't able to do that for whatever their entire existence up until a few years ago. I'm welcome to be corrected on that, but like that's my large scale impression, and maybe at some point we should like get some real robotics people who can like straighten me out or tell me that I'm right.
Yeah, so to
Oh,
modern control theory.
You were
And
frozen for 10 seconds, Eli. Can you repeat?
Prep. Okay, so I'm going to correct you a bit on and push back on the first point somewhat, just in the sense that if you look at controls and robotics conferences, like if you look at ICRA, I'm actually forgetting what the A stands for, sorry, but it's International Conference on Robotics and something, major robotics conference. They use machine learning a lot. they use lots and lots of machine learning and plenty of neural networks. They just tend to do model predictive control with it rather than RL. And these are two very subtly different formulations of optimal control. They're not horrifically different.
Okay. All right. In the interest of time, thanks for the discussion. Let's move on. We have a few more slides left. Next up is Fritz, who's unfortunately not here, so we'll skip. And okay, is there anybody who wants to challenge Tom? I have one question that I will ask, but I don't think it's fundamental. But you said that agents maximize empowerment. That's like for you, that's a central thing, right? Yeah.
Not on like a strong I'm not saying that this is like motivating all behavior all the time. No, I'm definitely not saying that.
Okay, but you did say that kind of empowerment maximization was central to you, and I'm trying to say I'm trying to come up with some thought experiment where destroying options rather than maximizing those options would be helpful. Like imagine if you're in a room and there's a lot of food there and you get hungry, maximizing empowerment means keep all the food with you, but survival means eat some of that food, destroy options. How can you reconcile that, your framework?
I think I didn't hear some part of what you just said. So you're saying I could destroy food. Why would I want to do that? I didn't catch that.
By eating it.
Oh, by eating it. But yeah, but like here's what I'll say about that. I mean, I think that empowerment, when scaled to very high dimensions, has a kind of frame problem. And so it can be that like there are biological pressures, right, on me that makes me hungry, and I want to get rid of that. And the act of eating, gets rid of that, and now I'm not hungry and I'm free to do other things. And yeah, that destroys options of what I can eat. But ultimately, I would say that you sort of have to answer this. It's hard to give a direct answer for this because it's ultimately you're at the mercy of like the structure of the agent and what is more salient, like having food as options available all the time or getting rid of some undesirable signal. So I guess I think that empowerment can handle these kinds of judgments, and that's why I like it, because I think it's really bad to have theories of intelligence that are based on Pareto frontiers of different values that you have to justify with other weighting mechanisms. So I would say that empowerment is good for avoiding these types of Pareto frontiers. Does that answer the question to your satisfaction?
What I'm hearing is that you're saying that empowerment is one important component out of many that competes with all those other policies. And sometimes you have to override empowerment to attend to the needs of homeostasis. And there's always going and competing.
I didn't say, what are the other pressures? I mean, I don't quite understand.
What I'm saying is that instead of trying to, I guess actually here I'm just channeling Anne a little bit. Instead of having one objective function, universal objective function that explains everything, we have multiple things competing at the same time, and the whole loss, the gradient descent, happens on a sum of many terms that compete with each other that ultimately explains behavior.
Right, but ultimately when you do that, you end up introducing some kind of convex combination and weights for that convex combination that are going to be state dependent. And so if you're like, as far as scientific modeling, this is kind of a nightmare because you're just pushing off the explanation to some new level of abstraction. I think I was listening to Tony Zader on Brain Inspired complain about this. And I think that, yeah, a lot of neuroscientists run into this problem with modeling.
Yeah. Okay. I guess. Yeah.
I guess I had one question for Tom about yeah, I'm just kind of curious. Of course, introspection can be a dangerous thing to rely on in neuroscience, but in terms of this kind of empowerment versus maybe more classic reward, when I kind of just think about it, the example you gave of like, why do you decide to move to a city or why do you, decide to do a PhD? I can kind of, it feels like that fits quite well with what you're describing in that I'm sort of mentally kind of simulating what that would give me and kind of what that would unlock and sort of playing that out. But it feels like a lot of things, maybe simpler things, you know, I'm not kind of eating because I think, oh, that's gonna unlock the ability later today to, do something. Um, and if that's modeled at the cortical level, it feels like if that kind of chain was necessary, then I would have some sort of kind of phenomenological experience of it or something. So it feels kind of like there might be kind of some things where it's I don't know, more evolutionary or something like that. I mean, do you accept that that's possible or?
Yeah, so I think that evolution can put fundamental pressures on you, such as like, oh, I need to get rid of this hunger, and you might have the instinct to interpret this as like, oh, one of many different types of drives, which it is, but like ultimately, um, such evolutionary pressures or signals like this that are disruptive can be, I think, interpreted in a kind of similar way. Like empowerment can work at the level of high level abstractions over long periods of time, but also like, oh, this is ruining my attention span, so I have to deal with it. So it all depends on the structure of the agent that is having to deal with these sort of evolutionary pressures.
Okay, yeah. I guess, yeah, it just feels like maybe it's kind of inefficient or that it's almost like kind of model based versus model free. That it's like if everything has to be model based, that's would just be kind of exhausting.
Yeah,
It kind of, yeah, but
yeah, I agree. I agree.
Thanks. Let's do the last slide. So, I think this is more of a question rather than a challenge, but and you emphasized the fact that the brain is a symphony. There's many things going on. It's a bag of tricks, and it seems like this is in contrast to the rest of the presenters who have been promoting some sort of grand unifying theory. Like RL says, maybe a unifying theory is that there's a reward that is being maximized. Active inference says there's free energy that is being minimized, and you explain everything with that. And Tom says it's empowerment, maybe. And there's all sorts of these like attempts at grand unifying theories, and you're saying no, let's just be calm and look at the data, and it's just a bag of tricks. So I want to understand, do you think that, let's say your results, do you think that they are not fundamentally amenable to a unified mathematical framework that explains them all, or do you think that we haven't found that yet?
Um, how about the laws of physics?
Okay.
I'm kind of joking, but like you can always embed things into a bigger theory, right? And then all the way up to the laws of physics, and we'll be fine, right? Yeah, so I think I'll stand by what I'm saying that I think before the laws of physics, I'll go to evolution, I guess, like that evolution, has put all kind of pressure on the development of our brain that supports cognition. And so, that has to explain to some degree the cognitive processes that support our learning. But even then, I don't think it's a grand theory because, I mean, it is a theory, but then it's acting in interaction with, the actual path that we've taken through evolution, which, is very random and has led where we are, but could have led elsewhere too, right? So, so I think in the end we need to, look at what we have and just my very strong impression is that what we have is, somewhat optimized for some aspects of our environment under, constraints that it hasn't converged, that it's, local optima, that there's resource constraints, et cetera, et cetera. So yeah, if I find and if someone was to find a theory that explained all of this, that would be great, but I don't think it has to be, and I don't think it's likely actually.
Okay, so if someone finds that theory, what are the features and characteristics of that theory that would make you feel satisfied with it?
um I mean, I would want some degree of explanatory power. I would want some degree of interpretability. Like by this I mean interpretability, um, um, in the sense that we can map a computational process, from cognition to the brain, through that. Obviously, predictive power. Um,
Okay, there you have it. Sorry, go ahead.
no, it's okay. Go ahead.
Yeah. Are you finished?
Yeah.
Okay, yeah, I mean, because you're running out of time, this is very interesting, but I wanted to, yeah, just conclude by saying, yeah, any people interested in grand unified theories, interpretability, explanatory power, predictive power. Those are the three things you have to aim for. And okay, before we move on to the last synthesis slide, I want to ask other presenters if they have any questions and challenges for Anne. All right. Okay. So now we arrive to the final part. And our debates. Now we want to come up with some synthesis that everybody's happy with. And honestly, I try to think about what could possibly unify all these diverse perspectives and very, very different angles. It's really difficult. And I came up with something which is, I don't know, trivial. I don't know. You might not even agree with that as well. Um, my proposal, maybe prediction error minimization can be a unifying theme, depending on what error is being predicted, what is being predicted, how's the error being computed, and how is it being minimized. And for instance, in maybe Adam says it's value, it's reward prediction error. Maybe Eli says it's the sensory state, divergence from a set point is the error. Maybe Fert says it's knowledge, prediction of information gain. We think about outcomes, option termination, empowerment, structure, sensory motor mismatch, killing hypotheses that don't match your motor actions ultimately. And then maybe you can say task state. I don't know. What do you guys think? Is this a good starting point for us to come together and agree on something?
Nope.
Okay, cool. That's what I want to hear. Why?
I mean, first, I would dispute my my line here. I was trying to figure out what you would come up with me because
It was hard, to be honest. Yeah, it doesn't fit, to be
yeah,
honest.
no, it doesn't fit.
Hadi, I apologize to say this, but this seems like a bit of a deepity. Like it
Okay.
seems like a bit of a fake insight in the sense that one, there's papers pointing out that
Yeah.
when you have any dynamical system that is stable under some Lyapunov function, you can write it as some kind of linearly conditioned gradient flow. Like that's a theorem. It's just true.
Right.
And then similarly, you're getting papers in the major machine learning conferences lately pointing out that, oh, everything is natural gradient descent.
Mhm.
And I'm actually thinking of there's like 3 to 5 different papers that are now saying this.
Mhm.
But, of course, if everything is just a preconditioned gradient flow on some, well, on some function, then like that's kind of a unifying theme, but it doesn't tell you much.
Right.
Like, how does that help you? If you're an engineer, how does that help you design something that you want to do gradient descent on, and then write an empirically useful optimizer that actually implements the flow in an effective way and does good credit assignment? And if you're a
Well, I think you're
neuroscientist, then or a behavioral scientist, how does that help you identify, the gradient flow implemented by the behavior you record?
so you're challenging the part where this becomes useful, not the part where this could unify things. You're saying that
Yes.
agree that there is some gradient flow on some Lyapunov function of some dynamical system. You're saying, okay, show me how to identify that function, show me how to implement it, how to optimize it, how to
Yes,
look
yes.
for it in the brain.
I've had to spend much of my time post-graduate school
Yeah.
digging myself out of believing in the free energy principle.
Okay.
So like
I appreciate your honesty, and I feel the same way. I think, the big challenge, sort of the meat of these grand unifying theories is not identifying. That's step zero. That's what I put on my slides. I don't know if you've ever seen them. It's step zero to identify those unifying themes. Step 1 to 1 billion, like the majority of the work, is actually providing meaningful meat to the theory. And the analogy I use there is this principle of stationary action from physics that states that physical systems follow dynamics that extremizes this notion, this mathematical entity called the action. And the meat is finding Lagrangians that actually map to real physical systems. That then you plug into that Lagrange equations that gives you the dynamics. So that took us maybe like several decades and several Nobel Prizes to find those Lagrangians that actually predicted things in the physical world. So I hear you. I totally agree with you that it's the hard part. But as a starting point, step zero, maybe that's what I came up with that could possibly unify us. So you're disagreeing with the utility of this, but Anne is disagreeing with the whole thing. So I want to hear how would you elaborate, Anne? Can you share a little more?
I'm not sure. I guess, I mean, I think what I said earlier that, I don't think there has to be a unifying thing, like comes from the fact that the brain, is developed through evolution in such a way that like nothing puts in there that there has to be some kind of, unifying principle for explaining cognition. So, if there is, it's kind of an accident in a sense, right? So it, yeah, does that help at all or?
Yeah, you're rejecting.
Yeah, I would
all the
agree.
premise. Yeah.
And I mean, and maybe I think when you say unifying here, I feel it also depends on kind of what is being unified. If it's saying, prediction error minimization is a way of kind of almost going back to the earlier task, like that's a way of explaining, the majority of human behavior or the starting point for developing any kind of useful AGI, then yeah, I would disagree. If the argument is prediction error minimization and also minimization, I feel like we could argue maybe over the meaning of that. But if kind of reducing prediction error is, if the question is that something that all of these kind of proposals have in common, maybe, I mean, yeah, at least in my case, or our case, like I would say that, yeah, the sensory motor mismatch, there is a prediction error there, and the system over time reduces the amount of that prediction error. Um,
Yeah, I'd even add to that by saying, maybe if we want to take, say, gradient flows as some kind of starting point in unifying theme, a step zero. Okay, step zero, everything is a gradient flow. But then or everything is gradient descent. We did this with deep learning the past 10, 15 years, and it turned out that the really useful step one was not to identify that you should do gradient descent. It was to invent batch normalization, drop out the atom optimizer, like gradient clipping tricks, and all of these 10 other things we keep in our toolboxes that actually make it practical to train a deep model by gradient descent.
Yep. So thanks for the clarification. I think this it seems like there's more disagreement in the synthesis part than the debate part. So I want to ask you another question that hopefully we can actually have some sort of synthesis. This was my plan B. If this fell flat, which it did. So plan B is that we're building this Frankenstein's agent, and we're gonna send it to Mars. We want this agent to survive. I want to ask each of you to add one component to this agent that you think is the most important component representative of your camp. Starting from top to bottom, Adam, go ahead.
Oh my God. All right. I mean, this is crazy. Come back to me.
Wait, of our own camp?
What are we starting
Because
from?
I kind of like the idea of picking another one. That like if I had to say what was, I don't know, something that I would want to integrate or something. But yeah, I don't know if that's a lot.
You mean like you want to choose something from another camp to integrate in your own model? What do you mean?
Right.
Yeah, that works too. Yeah, let's do it.
Okay.
We're
So
running out of time, but yeah, let's do it. Maybe
I guess the empowerment.
Yeah.
Empowerment. Tom's work on that and the option kernels seems interesting. So if if I'm working on something, I already have a lot of stuff at the moment, but we want to add something to let it survive on Mars. That seems like a concrete, interesting thing to bring in.
Thanks, Niels. Who wants to go next?
Can I go next?
Go ahead, Anne.
Yeah. So rather than adding from another camp, because I'll confess that I haven't done my homework and listened to everyone's talks. I'll start from existing AIs. And what I would add is a resource constraint, actually. Essentially, I think that when we are under pressure from resource constraints, we end up having to develop approximate mechanisms that do nearly as good, but not optimal, and that just work more efficiently. And so I don't know exactly what this would look like, but I think like thinking about resource constraints, capacity constraints, computation constraints, whatever, is the path forward to like, better overall flexibility, adaptability, etc.
That's a question about that, or is that going to completely derail us at this
Go ahead.
So, and I'm curious about how you think about resource constraints. Something that has never made sense to me, right? Is so we have however many billions of neurons and trillions of synapses in our brain, and then also we have a working memory capacity of 4 or 7 or whatever. So what's going on there, and what should I think of as the true constraint?
Yeah, I mean, it's kind of my big 30-year question actually, but I agree with you. It's like it seems crazy that with all those neurons you shouldn't be able to have a higher working memory capacity. And so I keep wondering whether it's a feature rather than a bug. And that creating again same as what I just said, that if you have a system in your brain that creates bottlenecks of information, it forces you to organize your information in such a way that it will pass through this bottleneck and in such a way that could, for example, promote generalization. It will lose your information, but it would keep you the most important aspects of the information. That can't work if it's the only thing you have, obviously. But again, if you have this messy system that has, this one has this constraint and that one has this other constraint, and they go together, then it might be the right way of forcing different types of information in different processes, such that when they come together, you're very efficient and flexible.
Thanks. Eli wants to go next.
Okay, so I'm going to add something pretty concrete to our little Mars robot. Interoception. Like there should just be temperature sensors, battery level sensors. We actually include all these things in modern electronics, but my point is, they should actually be inputs to the learning system to make sure that whatever learning algorithm it's using and whatever objective function it's optimizing, it knows that if it doesn't, get its solar panels into the light and charge up its battery, it's going to die and not be able to do its job anymore.
Beautiful. Actually, it connects nicely to Anne's point. If you have some sort of resource constrained computation, resource aware computation, when the battery is low, you switch policies and so on. So it's required to intercept, receive that. I don't know.
So I finally have my answer ready, which I think is very good simulation, which ideally you would be able to query before you're dropped on Mars. This is, I guess, analogous to two things. One is just evolution, right? Like it's like humans would do very poorly if you were dropped on Mars in a similar situation. We don't have however many millions of years of evolution to prepare us. And similarly, I think you would, a deep learning system would be fine if it had sufficient time and data to learn. If you're not going to allow it to do that when it gets there, because things are going to be hard.
Interesting. Sim to real. All right.
Plus extra bells and whistles.
Very nice.
I'll just build on Eli's suggestion, which is that I guess, I'll draw from my own camp in that I think it's necessary to represent temporal distributions of stuff, right? So you can reason about, am I going to run out of battery if I don't make it to this, back to the base in time, without experiencing it. And so I think treating, time as a variable and not, you don't want this, this agent on Mars to have to train a recurrent neural network, just to solve these sort of complex time-based tasks.
Thanks, Tom. Makes perfect sense. I think with that, we're already running a few minutes after the time. Is there any final thoughts and comments that anybody wants to add? Okay.
Thanks for organizing.
Well, thank you so much.
Thank you.
Yeah, thank you. That was a great idea.
Yeah, I really enjoyed. I learned a lot from you guys, and I really appreciate that you took the time to prepare and to present and to join us. And hopefully, we can actually have more of these meetings. Right after this, I'll share the current schedule for spring. There's a bunch of really interesting talks coming up. Like, for example, one thing that I'm very excited about is this paper from David Abel and others. It's called Three Dogmas of RL. And I'm very interested to hear about that. There's another paper down the line in May from Sam Gershman about subjective functions. These are very, very interesting conceptual ideas that I would love if you guys join and participate in the discussion when those talks come. But yeah, that's all I wanted to add. Yeah, thanks again. If I'm going to stop sharing right now.